Now I want to find moment of inertia with respect to this axis x. So this is the problem. So how can I solve this problem? First, I know that if I go to the appendix, I know that the moment of inertia is going to be integral over area y squared dA. So you find out this is the formula. But look, we have a little hole here. Is it good approach to do integration? No, the integration is going to be too hard. We don't want to waste our time. We just want to do it in a tricky engineering approach. So what's the approach if I don't want to do integration? Well, the approach is decompose this shape into simple shapes like circle, triangle, rectangle, that I can find the moment of inertia from the table. And look, I'm going to give all the formula you need in the exam, right? We don't need to memorize anything. So first of all, first step is decompose it into simple shape that you can find moment of inertia from tables. And then the second approach, the second step is to combine them together, right? So if you have hole, it's going to be negative. And if you want to transfer it, because you see, the formula that we have is with respect to its own local centroid, is not with respect to this shifted axis, right? So I have to use parallel axis theorem for every single of them to shift it to x and then combine them together. So that's the approach I need to do, right? So I make my table here, shapes. Let's say shape I. For shape I, then I have I x bar I, area I, and then dI, and that's the distance that we shift the local centroid to the x-axis, dI, right? Finally, the I that I'm trying to find, I x I is equal to I x bar I plus a I dI squared. Moment of inertia with respect to a shifted axis is equal to a moment of inertia in its local centroid x bar I plus area times the square of the shift. Alright? So all I need to do is fill up this table, and then at the end the sum of this column is going to be my final result. Record, and that's the moment of inertia with respect to x or x. Right? That's going to be ix. All right. So let's start decompose this into basic shape. So the first shape is the solid rectangle. And the second shape is this empty circle, the hole. Right? So my shape is equal to my composite. My composite shape is equal to 1 minus 2. Shape 1 subtracted by circle. Right? So this, don't forget this negative. So at the end, things here are negative when you add it together, right? So let's go to shape 1. So here, put 1, 2, and sum. So what should I put here? Local moment of inertia, a local centroid for shape 1. In fact, if this is shape 1, its local center is right here, right? All I need to do is to find moment of inertia with respect to the axis. Now it's the time to go to the appendix, or in exam, you go to the last page, and last page contains all the formula you need. So You go to, this is I guess page number, yeah, it's page number 815. Let's put it right here. Appendix B, and that's page 815. Right? This is X bar from here to here. Let's say is D from here to here. H, then X bar 112 B H Q. Alright, so that's for rectangle, and then page number 814. Then you have changing the different formula for circle. And you have Ix bar equal to pi over 4 radius to the force bar. So this is the shape. That's the formula. See that? All right. So let's use the formula. So if I have that formula, what should I put here? So I go to shape 1, solid rectangle, right? You see that? So my B is 100, H is 150, 75 plus 75, 150. So I put 112, 100 times 150 to the third power. That's the first thing. The area is equal to 150 times 100. And the distance, what should I put for D? 75. Now let's go to shape 2. Shape 2, pi over 4, 25 horsepower, area pi 25 squared, and D2. What should I put for D2?
25? No.
First of all, you ask, what is D? D, this is in fact used in parallel axis theorem, right? Which is this one, right? So D is the distance between two parallel axes that you shift. Look, for shape 1, right? My local, this formula 1 over 12, 100 times 150 to the third power is with respect to this axis. Let's check mark it. X bar 1. It's local centroid. The one I'm asking is with respect to this axis. So this is your shift, right? So D was this distance, which is 75. You can see here, right? For shape 2, you have the different formula, so it's pi over 4 radius to the fourth power, right here, right? So this is with respect to, again, the same axis, this one, x bar 2, but not this one. So you have to transfer it here. So what is D? How much you transfer it? 75. What am I missing here? Negative. So if you know that from the central computation, area was always negative. Right? Also this integral, because this doesn't exist, it's a hole here, right? It's empty. So if you do this integration, it's a negative sign. Right? So now finally let's compute this, the last column. So this one, the third column, is the first column plus the square of third column times the second column. So I can just fill it out. I can just put the formula and fill it out automatically. So let's fill it out. Going to be, first one is and the second one is going to be negative 11.4. Now, if you add them together, it's going to be 101.1 and 6. That's the final answer. So this is the moment of inertia with respect to this axis, x.
And that would be millimeters to the fourth, right?
Yeah. So the point is, whatever unit you have, if this is inches, that's going to be inches to the fourth. Millimeter, millimeter to the fourth. I basically factor out the unit. We save the ink, and sometimes unit is going to distract you. It's a lot of like. So now let's work on another example. The shaded area here, again, is a complicated geometry. So the integration is not a good option. So what should I do? Again, doing the same thing. Creating the table. So, first thing I do, first decompose it into simple shapes. The way I do it, I pick this one. First of all, before we actually do that, you ask what is the question? The question is find I moment of inertia with respect to x and I with respect to x bar. So you have two steps, two parts. This question has two parts, part A and B. Let's say this part A and B, right? And x is the axis going from here, the base, let's say this is x, and x bar is the axis going through the overall centroid. So this is over a centroid, and this is x bar. So total centroid. So I say find the moment of inertia with respect to these two axes. Again, what should I do? In step one, decompose this shape into simple shapes. So this, I take this as shape 1, and I take this one as shape number 2. That's what I think. You can take, you can change it. You can do this. You can take this one as shape 1, 2, 3, 4. 1, 2, 3, 4. Right? The idea is just decompose this complicated shape. Of course, it's not very complicated, but it still is not straight. It's not in a circle, rectangle, triangle, the basic shape. The idea is decompose it to simple shape so that I reuse the formula that I have in the appendix, right? And I can compute it without doing the integration. We don't want to do integration with this kind of geometry, right? All right. So again, you can also take this one as shape 1, and this one shape 2, and this one shape 3. You can do that too. So the choice of how you decompose this area is up to you. The final answer should be exactly the same. I recommend when you go home, do an optional homework. You don't need to turn it in. Take another configuration for yourself, fill out the table and see if your final answer is similar to what you're going to get right now. All right? So the next thing I do, I make a table. Let's put it here. Table. So ready? It's in here. So I ask you, what should I put here? So you go to shape 1. Which one is shape 1?
112 times 10.
Here. 112 times, and then you have 1 to the third power. Let's put it here so when you go home you can double check, make sure that how you got that number, right? Area 1, 10 times 1, and D1. First of all, I'm doing part A. So my axis that I'm transferring to is X, is this axis at the bottom, right? So what's my shift? How much I'm shifting it? You go to shape 1, where is the centroid? The centroid to shape 1 is right here, right? So the distance from the local centroid to the axis that I'm shifting is D. So what's D?
0.5.
0.5. So that's the first part, right? Now let's go to shape number 2. What should I put here?
1/2 2 or 112 2.
112 times
2 times 2 times
2. Is it just 2?
9 cubed.
Times 9 cubed. Again, you use the same formula here. You see it here, right here. 112, but look, the base here for shape 2 is 2, the height is 9, right? So 112 times 2 times 9, 2. Area, 2 times 9. Distance, that's the distance between the local centroid of that particular shape, to the axis that you are transferring to. So what should I put here? 5.5. 5.5, thank you. So why 5.5? Well, we go to shape 2, there you go. The local centroid is right here. Right? This is a local to shape only 2. The distance between this one and the one that I'm transferring. So from here to here is the entire thing 9 divided by 2, which is 4.5. Plus 1, 5.5. You see? Now, all I need to do is to just do this computation. Right? So let's do that computation. This one plus the square of this times this. Second one. Six. Look, this number is weird. It gives you exactly 6. So it may show up in the final exam. But look, I'm telling you, in the final exam, if you memorize, you won't be able to pass the final exam if you memorize it. You have to learn it. You have to know why I'm doing this. Under the hood, you have to know the concept. If you just memorize, okay, you put 5.5 there, and then you put, like that kind of the style that sometimes you see the student trying to memorize and going to tutor and trying to absorb the science. That's not going to work. You're going to fail the final exam. You have to learn it. Why I do this, right? Well, I'm not saying that you have to go too deep, like see how we got parallax theorem, the proof, right? That's too much concept, too deep. Maybe you didn't have time to go too deep like that. But at least you should know why we're doing like this. Why we're creating this data, why we don't do the integration. Like if I see, sometimes I see, like last time I did this quiz, and obviously doing integration for this is a pain in the neck, right? It's just stupid. And I saw some students like integral square root of x squared minus r squared over from here, and then plus integral from here. And I was like, look, that's not the correct approach. You may be able to do it, but this requires calculus number 6 to do, call it polar mapping, Crystal-Schwarz mapping, something that is very advanced for graduate schools. It's very advanced, like PhD thesis. So we don't want to do that. That's just obvious. That's the reason we invested a lot of time doing it. In the several classes we have been doing this because we don't want to do integration, right? That's the concept. So the final answer is going to be this one plus this one. And now it's time to double check. Do I have holes here, negative sign? No. There is no hole. Both of them are positive. Both of them are zero. Are the actual values. So let's just add them together. So we get 669.3, or simply 669. Now, if you look at the question here, if you have a part B, it says find the moment of inertia for this shape, but not with respect to x, but with respect to this axis that goes through the centroid, x bar. You see the centroid of the shape, not the individual shape, individual part, the entire thing. So what should I do now? What's the procedure? So the question is find the centroid with respect to this axis, the one that goes through the centroid of the entire shape. So what should I do? Well, when I did x, the first one, I knew where that axis was, right? I knew its location. Now the question is, if I want to find the moment of inertia with respect to a new axis, like the one goes through the centroid, I need to know where the location is. So I need to find the centroid of the entire shape before I do it, right? So now the question is, where is the centroid? More precisely, where is the y location of centroid? In fact, I'm trying to find the y location of the centroid. Well, it's a simple centroid calculation. Again, you go to the appendix, and you find out that the centroid, the formula is like this. X bar is equal to summation xi ai, summation ai, and y bar is summation yi ai, summation ai. This formula will be given in the appendix. Well, the one I want here is the y location. Well, the x location, we all know that is as 5, right? It's symmetric. So where is the y location? So I make my little table here for centroid computation. So you have shape 1, 2, AI, YI. This is what I need to compute, YY. So I need AI, YI, and then AI times YI. So for shape 1, area 1 is 10 times 1 is 10. And Y1, what's the centroid of Y location of centroid of shape 1?
0.5.
0.5. Thank you. Go to shape 2. Area of shape 2. 2 times 9, which is 18. Y location of the centroid of shape 2 with respect to the bottom from here.
5.5.
5.5. Yeah, 5.5. So this multiplied by this, put it in the third column, 5, and then 18 times 5.5. $99. So sum area is equal to 28. Sum of this column is 100. 104. Right? So the y bar of centroid is going to be 104 divided by 28. 104 divided by 28. 3.71. Let's put this 4 here. Keep 4 significant digits. So when we do all the computation, we end up with 3 actual accurate digits. So 3.714. Right? So from here to here is 3.71. So now you tell me, if I want to do part B, IX bar, what's going to change with compared to part 1, IX? Distance. You see, I'm going to have the same table. If I start from scratch, I'm going to have the same number of subshapes. I'm going to have the same local centroid computation. Because look, the formula is the same, and its local axis is always the same. Doesn't matter where you move your axis, right? The only thing that changes is the third column, right? So now you tell me for part B, IX bar, what should I put here and here? Well, if this changes, this depends on this 3 columns, right? So this will be updated automatically, right? So what should I put here?
5.5 minus 3.7.
Thank you.
Shouldn't that be for the second shape?
Oh yeah, it'd be.
Yeah, that's for second shape. Yeah, that's this is shape number 1. Yeah, we computed this for shape number 1. So this goes here 5.5 minus 3.71, and for this shape 2. Now for shape 1,
3.71 minus 0.5.
that's right. Is there anyone that don't know how I got this? This is extremely important. I can guarantee you will get a very bad grade in the final exam if you don't know how I got this.
So why? So it's just the scalar distance. Like it doesn't matter if it's below or above.
Well, let's put a negative. Let's put negative positive. But look, when we add together is d squared. So the sign is always positive. The sign doesn't matter for our purpose. You see? So if you just forget it, okay, it's positive or negative or whatever. If you put a negative here, the end result won't change because you have a square times d. You see that? Now let's do computation. So the first computed value for part A, let's put it here. It was 660. What was the value first one? 660.
669.3.
Okay, this now for the second one. First of all, before we compute it, what do I expect to get? Should I get a bigger value or a smaller value? If I move my reference axis to the center. So first, smaller, yeah. Imagine this is like your area, right? And your axis is at the bottom here. You see it has more moment, more torque from the area. Imagine area is like a weight. It has more torque or moment if your axis is here. Now when you move this axis to the centroid, right here, it's more balanced. The area is more balanced distributed around across that axis. So you should get a smaller torque. But this is kind of like torque. You see? Y squared dA. is just summation of y squared delta A over a small part. It's like computing the moment coming from a small chunk of area distributed, right? So I should get a smaller value. So what do I get? Let's fill out this one. So that's going to be yeah. And the second one is going to be $179. Again, it's time to check which one is negative, which one is whole. Well, we don't have whole. Both of them are real and positive, right? Now add them together. Then you get 280 something.
$283.
So the part B answer right here is going to be 283.1. So you can see the moment of area is decreased because the area is more balanced across that axis. It's not on one side, right? So I think it's time to close this class, and this could be like problem number either 684 or 690. 684, problem 684, problem 690. And these problems similar to that are in your study guide. So please watch the video when you first do it yourself. If you can't figure it out, watch the video and do it again. Try to master moment computation because this can be important. All right?